Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 11.9 from your textbook, investigating how power series, which we introduced in 11.8, can be used to represent functions. So, to start this off, let's go ahead and consider this specific power series. The power series, the sum from n equals 0 to infinity, x to the n. If you think about actually writing out the first few terms of that, this would look like 1 when n is 0, x to the 0 is going to be 1, and then plus x, and then plus x squared, and then plus x cubed, plus dot, dot, dot. So this is in some ways the most basic power series you can imagine. The a sub n in this case is just a constant value 1, so it's just all of these polynomial terms. Now, the interesting thing about this power series is that for this power series, any particular choice of x, if you choose an x value, this power series is going to become a geometric series. If you choose something like x equals 2, then what you have is you have the sum from n equals 0 to infinity of 2 to the n. That's geometric. If you choose like x is minus 1/3, then you get the sum from n equals 0 to infinity minus 1/3 to the n. So no matter what x value you choose, you're going to get something that's geometric in nature. So we know quite a bit about geometric series. For example, we know that geometric series converge when that common ratio in absolute value is less than 1. So we know that this will have a radius of convergence of 1. You'll have to choose an x value between -1 and 1 for this to actually be a convergent series. And we actually know the interval of convergence will be -1 to 1 with open parentheses on both -1 to 1 and 1. And that's because, of course, if we did x equals minus 1, we would get the sum from n equals 0 to infinity minus 1 to the n. That's alternating, but the limit is not 0, so it's going to diverge by test for divergence. And, of course, x equals 1 is just going to be the sum n equals 0 to infinity 1 to the n. That's a sum of an infinite amount of 1s. That's also going to diverge. So we know that this thing has radius of convergence 1 and interval convergence -1 to 1 with open parentheses on both. But actually, that's quite a bit that we know about this power series, but we know even a little bit more. Because it's a geometric series, we actually know how to sum up this series. If we're in that radius of convergence, where the absolute value of r is less than 1, we know that the sum from n equals 0 to infinity, r to the n, is 1 over 1 minus r. This was the geometric series formula. This is one of the first things we established way back in section 11.2. So we can say that as long as x is in the interval -1 to 1, as long as x is in that interval of convergence, the series is going to converge, and it's going to converge to 1 over 1 minus x. So in other words, the sum from n equals 0 to infinity of x to the n is equivalent to 1 over 1 minus x. Now, if we reverse this equality, obviously writing it in putting this one on the other side and this guy on this side doesn't change anything. But what we actually can do then is we can imagine representing the rational function, 1 over 1 minus x, that's a rational function, it's a polynomial divided by polynomial, as an infinite polynomial. Now this is sort of crazy here, because what we're basically doing is we're taking something that is a non-polynomial function, 1 over 1 minus x is a rational function, and we're writing it as an infinite polynomial. So this is our first example of representing a function as a power series. So we're taking something and coming up with a power series representation. In other words, we're taking a function that we might know from other sources, from other algebra discussions, whatever. 1 over 1 minus x is not a particularly crazy function. It's something we're pretty used to. We would know how to graph it, all that sort of stuff. And we're coming up with an equivalent representation, something that it is exactly equal to, in terms of an infinite series, a power series here. So it turns out, through some clever manipulations, we can represent many other functions as power series. So our sort of goal now in 11.9 is going to be to try to take functions that we've seen before, things like these rational functions, and then later on in later sections we'll look at things like e to the x and the trigonometric functions, etc., and we'll try to represent them as these power series. Now, one thing that we do want to make special attention to in this little discussion here that is very important is at this moment right here where we say that 1 over 1 minus x is equivalent to this power series, we do have to remember that that is only true if we're working on this interval. So we should make a comment that this is for absolute value x less than 1. So as we begin to do our examples, not only are we going to be interested in trying to represent functions as power series, but we want to know where those representations actually hold. Okay, So let's see what these sort of clever manipulations sort of look like. So, I mean, this one we got very lucky because we just based it off of the geometric series formula that we already learned. But let's see how we can sort of make use of this to build some other representations. So let's try to determine a power series representation for the following function and then state the radius of convergence. We could do interval of convergence as well, but we're mostly just going to be interested in the radius of convergence. So our function here, f of x, is 1 over 6 plus 2x. It's another rational function. So let's see if we can come up with a way to sort of approach this. Our idea is that we'd like to get this into a format where we can use the one established result we have so far. This is our one established result. 1 over 1 minus x is equivalent to this power series. So we want to try to build something that looks like this, and then we can make our jump to a power series. So let's look at what we have here. We have 1 over 6 plus 2x. Well, we remember we want to sort of get that to look like 1 over 1 minus x. So maybe the first thing we do is we want to try to get that to be a 1. So let's go ahead and factor out a 1/6. So we can imagine this as 1 over 6 times 1 over 1 plus, and then when we factor this 6 out of 2x, we're actually going to get something like x over 3. Now that looks a little funny because it's built a complex fraction. There's a fraction in the denominator, but at least it gives us our 1 there. Now, the other thing that we want to achieve is that we want it to be 1 over 1 minus x. So we'd like this to be sort of a negative expression. So we can introduce a double negative to do that. So let's have this be 1 over 6 times 1 over 1 minus negative x over 3. And of course, that's legal, right? We can think about that plus x over 3 as minus x over 3. Okay, now to really sort of cement this next step, let's go ahead and use a substitution. Substitution is such a powerful technique. You guys have seen substitution in differentiation, in integration, in so many different places. Let's use it here as well. Let's let z, some new variable, be that negative x over 3. So notice then that what we have is we have 1 over 6 times 1 over 1 minus z. And now this expression right here is exactly the one expression that we know a power series representation for. So let's go ahead and use that. So we can then say that this is equal to 1 over 6 times the summation from n equals 0 to infinity, z to the n. Now, this is really important. This moment where we go from the function to the power series representation, this is where we also have to make sure we state that radius of convergence. And we know that this transformation from going from here to this holds as long as the variable, in this case z, in absolute value is less than 1. So this holds for z less than 1 in absolute value. Notice I didn't have to mention radius of convergence anywhere else until right now because this was the moment that we introduced that infinite series. Okay, now obviously we need to get back to our original variable, so let's replace that minus x over 3 in there. So we can say that this is 1 over 6 times the summation, n equals 0 to infinity, minus x over 3 to the n, and let's do the same thing and plop that in here as well. As long as the absolute value, negative x over 3, is less than 1. Okay, now we can do some simplifications to make this look like a more normal sort of power series. We can say that this is 1 over 6, and then the summation n equals 0 to infinity. Let's distribute this n to each piece. Keep in mind that when it goes on that negative, it'll form an alternating piece. So we can imagine this as minus 1 to the n over 3 to the n and x to the n. And notice that that resembles a normal power series, right? There's the a sub n, and there's our x to the n. Now, could we rewrite this in different ways? Sure, we could call it minus 1/3 to the n as well. Doesn't matter how you want to write that. Over here, though, we can actually solve this for x. We can multiply the 3 over, and then realize that the absolute value of negative x is just the same as the absolute value of x. So we get that the absolute value of x needs to be less than 3. Last thing we can do, I suppose, is just move this 1/6 inside, and we can view this as the summation from n equals 0 to infinity, 1/6 times minus 1 to the n over 3 to the n, x to the n, as long as absolute value of x is less than 3. So this right here tells us that our power series representation, this power series, matches the function that we were looking at, 1 over 6 plus 2x, as long as the absolute value of x is less than 3. So this tells us that our radius of convergence is equal to 3 here. So what we just did here is we built a power series representation. We built an infinite polynomial representation for this rational function. And the way we did it was by manipulating the expression into the one expression that we know how to represent as a power series, 1 over 1 minus a variable. Then we made that jump from here to that power series representation, and then we unpacked our substitution. Notice that because we substituted, it also did impact the radius of convergence, right? The radius of convergence was no longer 1, it was now 3, because we actually needed that negative x over 3 to be inside that interval -1 to 1. Okay, so this is our first new example of building a power series representation of a rational function. Let's go ahead and take this a step further and use this to build another representation. So we're going to use the previous example to determine a power series representation for this function, g of x equals x cubed over 6 plus 2x, and then state its radius of convergence. So let's think about how we could do this. And if we have x cubed over 6 plus 2x, let's rewrite that for a moment and view that as x cubed times 1 over 6 plus 2x. Now, of course, we have a massive hint here. We're saying use the previous example. And remember, in the previous example, we built a representation for 1 over 6 plus 2x. So we can then go ahead and say that this is equal to x cubed times that summation from n equals 0 to infinity. And we're just going to use this exact expression. So that 1 over 6 minus 1 to the n, 3 to the n, x to the n. And this moment where we say that this can be replaced with this power series, remember that only holds on a certain interval, in this case, absolute value x less than 3. Okay, now notice we have this x cubed outside, but we can distribute that in. Multiplication certainly distributes over addition, and this is an infinite addition. And this thing here would mix with this. Since they both have the same base, we would add those exponents, and we would get that this is n equals 0 to infinity, 1, 6 minus 1 to the n over 3 to the n, x to the n plus 3. And that's, again, as long as x is less than 3 in absolute value. So we had a new rational function, x cubed over 6 plus 2x, and we came up with an infinite polynomial representation of it using this power series. Notice it also had the same radius of convergence as the previous one. The radius of convergence here is still equal to 3. Okay, so these were just two quick basic examples here to show you guys some of the manipulations we're going to be using with power series. Let's go ahead and summarize this and then take a look at one more example. So, to summarize the previous two examples, we've seen some basic manipulations useful for building power series representations of functions. The first manipulation that we learned was substitution. We can substitute as long as our substitution is a polynomial with the same center as our power series. So there's a little bit of sort of subtlety to the substitutions you can do. You'll notice that when we did our substitution here, my substitution was z equals negative x over 3. That's really saying z is negative 1/3 x. Notice that this is a polynomial. Right? That's definitely a polynomial. It's linear. And the center of this polynomial is 0. Which is the same as the center of our power series. So that would be a legal substitution. We would not be able to do a substitution like z equals sine x, because that's not a polynomial. And we wouldn't be able to do a substitution like z equals x minus 2, because while that is a polynomial, the center there would be x equals 2, and the expression we have has a center at 0. So it's got to be a polynomial substitution, and it's got to have the same center as our power series. As we saw, substitution can change the radius of convergence. In that example, the radius of convergence of the original power series was 1, but after the substitution, the radius of convergence for our power series was 3. So substitution is a very useful manipulation for building power series representations based on representations you already know. The second manipulation we saw that's a valid manipulation is multiplication. We can multiply a power series by a polynomial term with the same center as our power series. That's what we did here. Here we multiplied it by x cubed. That was a legal manipulation because x cubed is a polynomial. Check. And of course, the center for this is 0, which is the same as the center here. We would have not been allowed to multiply by like sine of x, because sine of x, again, is not going to be a polynomial. And we wouldn't be able to multiply by like x minus 5, because x minus 5, while it is a polynomial, has a different center than our power series. So we've got these two manipulations, but we do have to understand there's some restrictions behind the scenes. You're really only allowed to work with polynomials that have the same center as your power series. And the reason is, if you don't do that, well, then that power series isn't going to necessarily be a power series anymore. So unless you do the manipulations as described here, you're not going to keep the actual power series structure. You might build another type of infinite series, but it won't be a power series structure. Now, later on in our next video, we'll take a look at another type of manipulation based on calculus, and we'll actually see that you can differentiate and integrate these power series as well. So these are not the only two manipulations, they're just the two that we've discussed so far. Before we get to talking about differentiation and integration of power series, though, I'd like to do one more example, sort of practicing these two manipulations and making sure we really understand what we mean by a power series representation. So let's take a look at one more example here. So we'd like to determine a power series representation for this function, 3x squared over 8 minus x cubed, and then state the radius of convergence just as before. So let's start with the same sort of approach of trying to manipulate it into a form where we can make that power series jump. So we've got our 3x squared over 8 minus x cubed. The first thing we can do is we can put that 3x squared sort of in the front and just look at the 1 over 8 minus x cubed. Right? And the idea here is if we can come up with a power series representation for this, then we should be able to multiply the 3x squared in, because that's a polynomial term with a center at 0, should be all good. So then we need this to be in the format of 1 over 1 minus z. So we need to factor that 8 out. So let's go ahead and write this as 3x squared over 8. And then after we factor that 8 out, looks like we get 1 minus x cubed over 8. Now we can see the substitution that we would like to do there. Let's go ahead and let z equal x cubed over 8. So out front, we still have 3x squared over 8. We're not going to bother substituting that because we know we're eventually going to go back in terms of x. And then here, we're going to have 1 over 1 minus z. Now we can go ahead and replace this. This is our moment where we actually introduce our power series representation. So this is going to be 3x squared over 8. And now we can replace this with the summation n equals 0 to infinity, z to the n. Right now, this is the only established power series that we're consistently using. 1 over 1 minus z goes to this sum n equals 0 to infinity, z to the n. Remember, that came from the geometric series formula. Later on, we will come up with some other sort of classic established formulas that we can manipulate off of. But for right now, the only one we have is this 1 over 1 minus z can be rewritten in this form. Now, the moment you introduce that power series, you also have to make sure that you're within that radius of convergence. So we know that this holds as long as z in absolute value is less than 1. Okay, let's go ahead and go back to replacing everything. So we have 3x squared over 8, and then we have the summation n equals 0 to infinity. Let's go ahead and replace z with x cubed over 8, and then all to the n. And then we also have to do that here. Absolute value x cubed over 8 is less than 1. Okay, now we can work on all these sort of pieces. Let's first distribute this n power onto both. And we can view this more as 3x squared over 8, sum n equals 0 to infinity. I'm going to view it as 1 over 8 to the n, and then I'll just put my x to the 3n over here. And I like to always put the sort of power series component, the x component at the end, and then put all the numeric stuff in front. Again, that's just a style choice. Doesn't really matter how you write it out as long as you're distributing that exponent. And we want to distribute the exponent because we're about to bring this stuff in and then simplify. Over here, if you want, you can multiply the 8 over, and you can get that the absolute value of x cubed is less than 8. All right, now we have some manipulations here. Let's bring this stuff in and multiply everything out. So we should get the sum from n equals 0 to infinity. The 3 doesn't have anything to mix with, so I guess we're just going to end up with a 3 up top. 8 times 8 to the n, well, this is an 8 to the 1, so it's going to add 1 to that exponent, 8 to the n plus 1. And here we have an x squared and an x to the 3n. It's going to add 2 to that exponent, x to the 3n plus 2. Then, of course, here we could cube root both sides, and we'd get absolute value x less than 2. So there we go. There's our power series representation. We can say that this function here, 3x squared over 8 minus x cubed, so 3x squared over 8 minus x cubed, is equal to the summation n equals 0 to infinity, 3 over 8n plus 1, x to the 3n plus 2, as long as we're operating on the range absolute value of x less than 2. Okay, so this, again, computationally, just practicing the two manipulations we've discussed so far, we had to do a substitution, and then we also had to do a multiplication by a polynomial term that had the same center. We did both of those, and we built a power series representation for this rational function. Okay. We're almost ready to start talking about the other manipulations, differentiation and integration, and talking about how calculus sort of applies to these power series. But before we do that, I'd like to just take a little bit of a closer look at this right here. What exactly does this equality that we just established really mean? So let's go ahead and talk about that just for a couple moments. So, what does representing a function by a power series really mean? Well, let's consider our previous example where we had that function, 3x squared over 8 minus x cubed. So down here, you can see a graph that I did of f of x equals 3x squared over 8 minus x cubed. Remember, this is a rational function. At x equals 2, it has a vertical asymptote, which you can see there. I also, because we're going to be talking about radius of convergence too, I put on vertical lines at -2 and 2. So we're really going to be focused in here. And these blue parts of this graph just represent that function f of x. Now, we found in our previous work that we did right here that this power series can be represented, or this function can be represented as the power series sum n equals 0 to infinity, 3 over 8 to the n plus 1, x to the 3n plus 2 with radius of convergence 2. So we're going to try to investigate what this really means. So the first thing I'm going to do is let's imagine actually writing out a few of these sort of terms. So if we think about this summation, n equals 0 to infinity, 3 over 8 to the n plus 1, x to the 3n plus 2, well, what happens if we just write out sort of the first couple pieces of this? So this, if we do n equals 0, would be like 3 over 8 x squared, and then plus when n is 1, we'd have 3 over 8 squared x to the 5th. And then when n is 2, we'd get 3 over 8 to the 3rd, x to the 8th, and then plus dot, dot, dot. So remember, we're saying that this function is equivalent to this infinite series. So it should be roughly similar to this finite function. So let's go ahead and first start by just comparing this thing to our first term. So we're going to ignore these other ones. Remember, there's an infinite amount of stuff, so we're going to do a very rough approximation. Let's look at this function compared to just this first term. So if we do that, I've gone ahead and graphed f of x, that's our rational function, which is the first term of our series, 3 over 8 x squared. So that 3 over 8 x squared, that is in red. So you can see that that makes a parabolic shape. And what I want you to notice is that in this area, it's a pretty good approximation. You'll notice that the red curve is very similar to the blue curve. Now, as you get over to here, you'll notice that the blue curve is up here and the red curve is this way. They're quite different for values like, say, 1.5 or something. 1.5 for f is there, 1.5 for our approximation is there. Same thing over here for like negative 1.5. Our red function is there, our blue function is there. They're pretty different. Notice they're super different out here. I mean, this guy's way up here and this guy's down here. But again, we're working within that radius of convergence from -2 to 2. And remember, this is only the first term of our series. So now let's go a step further and use the first two terms of our series. So now 3 over 8x squared plus 3 over 8 squared x to the 5th. Now that's still a polynomial, and I still went ahead and graphed it in red. And what you'll notice is that now that red function is very close to the blue function, again in that -2 to 2 range. Now, when you get really close to -2, you'll notice that they start to get a bit different. And again, when you're a little past 1.5, the blue and red start to be pretty different. But again, remember, this is only the first two terms. The main idea, though, is that these first two terms are a very good approximation in here. All right, let's go one step further and compare f of x with the first three terms. So now we're going to compare f of x with the polynomial that's the first three terms, 3 over 8x squared, 3 over 8 squared x to the fifth, 3 over 8 cubed x to the eighth. So there it is in red again. So this is again graphed in red. And you will see that this time it is very good as an approximation until very close to -2 and until very close to +2. So in other words, what's going on here is that as you extend that infinite polynomial with more and more terms, it becomes a better and better approximation. It doesn't approximate f of x everywhere, but it becomes a better and better approximation on your radius of convergence, which in this case was from -2 to 2. So in general, our sort of summary here is that our infinite series, if we lop them off and treat them as a finite series, they become better and better approximations as we add more and more terms. And in theory, again, this is a theoretical concept because we can't have an infinite amount of terms, but if we actually had the infinite series, it would actually be an equivalent function to our original f of x, our rational function here. So the big idea here is that we're coming up with this infinite polynomial that approximates our function perfectly on the actual radius of convergence. Now, of course, if we cut that polynomial off and we only look at a handful of terms, it's only an approximation. But as you can see, even with just the first few terms, it's a pretty good approximation. And actually, by the very end of chapter 11, we'll actually learn how good of an approximation this sort of truncated series actually is. So I wanted you guys just to see these graphs to really understand what we're doing when we talk about a power series representation. We're trying to come up with a polynomial that matches our function as best as possible. It turns out that that's only doable if we do an infinite amount of terms, but it can be a pretty accurate guess even with just a few terms. In our next video, we'll be moving into the second half of section 11.9, and we'll take a look at how calculus, specifically differentiation and integration, works on these power series.